Assalamu alaikum. Today's lecture, we are going to talk about the wind turbine. First of all, we start with the introduction to wind energy. This is a quick question. What is the maximum efficiency of energy generation using the wind? What do you expect? Answer is 60%. The maximum efficiency of energy generation using the wind cannot exceed 60%. Historically, there are some kind of development of wind power. Since 1995 up to 2011, there is a global installed capacity of wind turbine grew by a factor of 10 over last decade. So this is why it's important to study the wind turbines and use it for electricity generation. What is the origin of wind? Wind is the atmospheric air in motion. The solar radiation differentially absorbed by Earth's surface, converted through convective processes due to temperature differences to air motion. There are some special scales of wind systems and a sample of associated wind types. There are different scales like planetary scale, synoptic scale, mesoscale, microscale. Planetary scale, the wind types global circulation, and its length scale up to 10,000 kilometers. Synoptic scale, like weather systems, different types of weather systems, and its length reaches to 1,000 kilometers. For mesoscale, this happens in regional, orographic, or thermally induced circulations from 10 to 100 kilometer length scale, and microscale at the end. It's like local flow modulation, boundary layer turbulent gusts from 100 to 1,000 meter. So these are different types of special scales of the wind. Now we are talking about what makes wind. First of all, you have the sun shines on land and water. Then the land heats up faster than water. Warm air over land rises up. Cool air over the water moves in, and so on. This will make circulation for the wind, and this will make wind happen. This picture actually states the global wind patterns, and we can see that there are some kind of high pressure here, and there are different types, or like troposphere in Arctic zone, troposphere in temperate zone, mid latitude layer, intertropical convergence zone, and so on. So this will give you some indication about the which areas in the world has high winds compared to other regions. Historically, we can talk about the history now of wind energy. In 5000 BC, Sailboats used on the Nile indicate the power of wind. In 500 to 900 AD, first windmills developed in Persia. In 1300 AD, first horizontal axis windmill in Europe. In 1850s, Daniel Halliday and John Burnham built Halliday Windmill, start U.S. Wind Engine Company. Late 1880s, Thomas Perry conducted 5,000 wind experiments, start Aeromotor Company. In 1888, Charles Rush used windmill to generate electricity in Cleveland, Ohio. Early 1900s, windmills in California pumped salt water to evaporate ponds. In 1941, in Virginia Tech, Grand Baz knob turbine supplies power to town during World War II. In 1979, first wind turbine rated over 1 megawatt began operating. In 1985, California wind capacity exceeds 1,000 megawatt. In 1993, U.S. Wind Power developed first commercial variable speed wind turbine. In 2004, electricity from the wind generation cost 3 to 4.5 cents per kilowatt hour. In 2013, wind power provided over 17% of renewable energy used in the United States. So this is the timeline of the history of wind energy. And here it's a brief history talking about the early systems. The first wind energy system has been discovered in the ancient civilization in the Near East or Persia. Vertical axis windmills, sail connected to a vertical shaft connected to a grinding stone for milling. Wind in the Middle Ages. These are some kind of winds in the Middle Ages introduced in Northern Europe. Horizontal axis windmill, sails connected to a horizontal shaft on a tower encasing gears and axles for translating horizontal into rotational motion. And finally, wind in the 19th century United States, windrows. This is called windrows. Horizontal axis water pumping windmills found throughout rural America. In modern era, there are key attributes of this period. Scale increase, commercialization happen, competitiveness, and grid integration. These are different type of improvement in the basic or regular wind turbine. Catalyst for progress: economics, energy independence, environmental benefits. These could affect the use of wind turbine. Turbine standardization happened also in the modern era. It becomes three blade upwind. This is a standard type of wind turbine. Horizontal axis on a monopole tower. Why wind energy? Why we are interested in talking about the wind energy? Because they are clean, zero emission of SO2 or CO2 or CO or NO chemical compounds, air quality, water quality, climate change, reduce fossil fuel dependence, energy independence, domestic energy, national security, and renewable, no fuel price volatility. So this is why there is a great interest in using the wind energy in electric power generation. And we can see here is the hydropower in blue, biomass in green, geothermal in red, in wind this is the light blue, and we can see that this wind interest in the wind energy increases from year to year compared to other renewable energy systems. In the United States, electricity generation from 2005 to 2015, we can see that the wind energy has a great interest in United States to be used for electricity generation. In China actually leads the world in the wind capacity, because the top 10 cumulative capacity, China the first, then United States, Germany, India, and so on. And here is the list of the countries. Number one in the world is China. It generates 188 megawatt from the wind energy. United States generates 89 megawatt. Germany 56, India 32, and so on. Let's talk about the types of wind turbine. There are two main types of wind turbine. The first type is called horizontal axis wind turbine, HAWT, and vertical axis wind turbine, VAWT. The horizontal axis has two types: upwind horizontal axis wind turbine and downwind horizontal axis wind turbine. The upwind, that the wind is coming from this side, from its front side, where the downwind, the wind coming from its backside. And the Darius vertical axis wind turbine had this structure. For short, these are the blades, rotor blades here. These are the nacelle here, and there is the gearbox generator here, and the guy wires here. So the modern wind turbines can be categorized into two classes based on orientation of the rotor. If the rotor rotates horizontally, so it becomes horizontal axis wind turbine, and if the rotor rotates vertically, so this becomes vertical axis wind turbine. The advantages of vertical axis wind turbine: it's omnidirectional. That means accept wind from any direction. Components can be mounted at ground level. Ease of service, lighter weight towers. Can theoretically use less materials to capture the same amount of wind. But they have different disadvantages, like rotors generally near ground where the wind is poorer. Centrifugal force stresses blades. Poor self-starting capabilities. Requires support at the top of the turbine rotor. Requires entire rotor to be removed to replace bearing. Overall poor performance and reliability. So this is why we are going to focus on the horizontal axis wind turbine, which is much better compared to the vertical one. The horizontal axis wind turbine has three different categories: small one, intermediate one, and large ones. Small one can be used to generate electricity less than 10 kilowatts. This can be used in homes, farms, remote applications, water pumping, telecom sites, ice making, and so on. For intermediate horizontal axis wind turbine can be used to generate electricity from 10 to 250 kilowatt. This can be used in village tower to generate village power, hybrid systems, distributed power. For large wind turbine can generate more than 250 kilowatt up to 2 or more megawatts. This can be used in central station wind farms, distributed power schools. The large wind turbine, actually common utility scale turbine, base two blade 100 meter, each blade length 34 meter, total weight 200 tons, foundation 6 meter, rated power from 1.5 to 2 megawatt, supply power to about 500 volts. And we can see that this turbine, this wind turbine has the length, have big length that can reach more than 150 meters. Wind turbine components, we can see that A is the blades. A are the blades. B, which is here, is the hub. C in the back here is the nacelle, and D is the tower. Actually, nacelle is the French word. It's meaning small boat. Houses the mechanical drive train like rotor hub, low speed shaft, gearbox, high speed shaft, generator. Controls yawing system. And nacelle, it contains most of the components of the wind turbine. The principal component of wind turbine, this is in details. Here you can see the blades, the wind direction, and from the below, from the bottom, the tower, the yaw motor, yaw drive, and here is the brake. In the back there is, or in the this is the front actually, the blades and the rotor. Then there is a low speed shaft, and here is the brakes. After that there is a gearbox that will convert the low speed to high speed, and then the high speed shaft is connected to the generator, and there is a controller connected to the anemometer, which is used to measure the speed of the wind. So everything are installed inside the nacelle. This is the nacelle, and there is in the front of the, or in the back of the wind turbine, there is a wind vane. So the yaw system of wind turbines is the component responsible for the orientation of the wind turbine rotor toward the wind. So yaw system is going to rotate the wind turbine and make its orientation in front of the wind or towards the wind. Wind turbine component, here are the rotor, nacelle. The rotor, this is an example of one wind turbine. Its length, it's almost like the Warsham field of football field. Its rotor, 35 metric tons, 77 meter diameter. The nacelle, 52 metric tons. It generates electricity 1.5 megawatt. It to deliver electricity to 1,200 to 1,700 household. The tower with more than 120 metric tons from 60 to 100 meters. And to see how it is big, this is the car here, and this is the our wind turbine, so it's much bigger compared to the car and for ski. This is the car is used here for ski. So how does a turbine work? This is a good question. So how does a wind turbine work? First of all, the inflow of wind coming here, this will try to, the inflow of wind activate the rotor A and blades B. Then once it rotates, the rotor and blades spin the main shaft, or they will spin the main shaft C, and the gearbox D, which spins the generator G, resulting in electric power output. Installation of a wind turbine. When you are trying to install a new wind turbine, it becomes separate in pieces, and then you are going to connect them together. First of all, you build the foundation, and then you install the tower, and after that you connect the nacelle and the blades on the top. And here you can see the blades on the wind turbine used for the wind farm, and the length of the wing on a commercial jet fighter. Increasing the size of the wind turbine. Here, by increasing the size of wind turbine, you are increasing the output power generated from it. Like this is 1 megawatt Mitsubishi with 62 meter diameter. When you increase the diameter of the wind turbine, 82 meter diameter, like Siemens, you are generating more power, more electricity, 2.3 megawatt. If you increase more the diameter, like 113 meter, you are generating more power, 3.6 megawatt. And the biggest one is with the 164 meter diameter, it generates 7 megawatt. It belongs to Vestas. Vestas 7 megawatt wind turbine. This is General Electric 3.6 megawatt wind turbine. So by increasing the diameter of wind turbine and its height, so you are increasing the power generated from it. Here, wind turbine perspective, there are some workers installing a new wind turbine here, and you can see that how these workers look like on the top of the wind turbine. And these are the blades with the 112 feet long, nacelle 56 tons, and the tower here. And the workers are working or are installing or maintaining the wind turbine. So the wind farm is going to be used to increase the electricity generated from this wind energy. So the turbine wind farm are going to connect the wind turbine together to increase the electricity generated. Offshore wind farm. The first US offshore wind farm is Block Island Wind Farm, located off the coast of Rhode Island. This 5 turbine 30 megawatt wind farm began operating in 2016. Residential wind system and net metering. Here is the wind turbine is connected to, it generates DC voltage input that will that will input the inverter and interconnect. Then the output is AC voltage. It will input the main utility breaker panel, and then it goes to AC electrical circuit or AC metering, and then connected to the AC to the grid. This is the system for residential wind system and using net metering. As we mentioned before, the component of wind turbine, again, tower that supports the weight of the turbine mechanism and absorbs loads put on the turbine by external forces. The nacelle attached to the tower rotates towards wind to maximize rotor speed, houses generator assembly. Blades design generally uses lift, the creation of high and low pressure zone from the wind to move the blades. And finally, rotor holds blades, rotates in order to run generator to produce power. So these are the main components: blade, nacelle, tower, and inside the rotor there is a hub casing, spinner, hub casing, and main bearing, main shaft, gearbox, generator, and so on. In this slide, we are going to talk about the wind turbine power curve. The maximum conditions for most windmills are around 35 to 55 miles per hour. Slower speed decreases the power output drastically. For example, if the wind speed decreases by half, then the power output decreases by a factor of 8. Obviously, every windmill has a different power output at different wind speeds, but most follow the trend shown below. We can see here there is a cut-in speed. Below cut-in speed there is no output power. After cut-in speed there is the power increases exponentially. When it reaches to the rated output speed at rated output power, the power saturates until it reaches to cut out speed. Cut out speed, you have to shut down the turbine. Here is a comparison between traditional and modern wind turbine. Below are some examples of wind turbine is used today and in the past. This is one kind of new modern wind turbine. This is another shape of new modern wind turbine. Compared to this, the old one, and this is the standard one. Future wind turbine. Scientists and researchers now are working on improving the wind turbine for the future to become more practical, more aesthetically pleasing, could lead to more desire, but the disadvantages could be produce less energy, costs could outweigh most of the benefits. The challenges of building the wind turbine is the wind pattern are never certain. Costs could outweigh benefits or take too long to pay off. Maintenance prices could be high because of new market, difficult to be approved, or in many neighborhoods. These could be the challenges. Then we are moving to the next section, power in the wind. These are the fundamental equation of the wind power. The wind power depends on the amount of air, its volume, the speed of air, its velocity, and mass of air, its density, flowing through the area of interest, which is called flux. From the kinetic energy formula or definition, we said that Ke equals half mv squared. And the power is the kinetic energy per unit time. So the power becomes half m, the first derivative of m times v squared. The first derivative of mass, we call it the mass flux, which is dm by dt. We call it mass flux. From the fluid mechanics, it gives the mass flow rate. Mass flow rate is the density by the volume flux. So dm by dt equals rho times A times V. So then we are going to remove dm by dt from the equation, power equation, and we put rho AV, so we get half rho AV cube. So that means the power from the wind turbine depends on the cube of the velocity, depends on the air density, depends on the rotor swept area, A, which is pi r squared, and r the radius of the length of each plate or the radius of the swept area. Power in the wind per square meter. In this table, it shows the power in the wind per square meter of cross section at 15 degrees centigrade and 1 atmospheric pressure. When the wind speed 0, you are expecting the power to be 0 here, like this point. When the wind speed starts increasing meter per second or mile per hour, the power increases. And when the wind speed increases with a small amount, the power increases drastically or too fast, because it has exponential relationship, cubic relationship. So it takes this trend. This is the relationship between the power generated and the wind speed. The swept area of Darius rotor, how to calculate it? The swept area of a vertical axis Darius rotor is a bit more complicated to figure out. One approximation to the area that it is about 2/3 the area of a rectangle, with the width equal to the maximum rotor width and the height equal to the vertical extent of the plates. That means the area, swept area of this type of wind turbine, we can use this formula, 2/3 d times h. So 2/3 d, the diameter, times h, the height. This is an example. If the air velocity is 5 meters per second and the air density is 1 kilogram per meter cube and the rotor radius is 0.2 meter, so the swept area, as we mentioned before, it's pi r squared. So we get pi r 0.2 squared, so get 0.125 meters squared. Once you know the swept area, we can calculate the power in the wind. So half rho AV cube. V is given, A is known, rho is given, so we can multiply them together to end up with the power from this wind turbine, 7.85 watts. Another example, compare the amount of wind energy at 15 degrees centigrade, 1 atmospheric pressure, that passes through 1 meter squared of cross-sectional area for the following wind regimes. First of all, we have 100 hours of 6 meter per second winds. We have another scenario, 50 hours at 3 meter per second plus 50 hours at 9 meter per second. So the average wind speed becomes 6 meter per second. For the first scenario, how to calculate the amount of wind energy. The wind energy, as we mentioned, it's the power times time. Power, we said half rho AV cube times the time, delta T. In the first scenario, we have to calculate the power, then we multiply it by the time. It's given 100 hours. So, in the first scenario, we have 6 meters per second in time 100 hours. So you write down half rho A V cube delta T, which the V is 6 meters per second and delta T is 100 hours. So when you multiply them together, you end up with 13,230 watt hour. This is the energy, the amount of energy produced by this turbine that is working at 6 meters per second for 100 hours. For the second scenario, you have two different speeds with two different times, 50 hours at 3 meters per second and 50 hours at 9 meters per second. So what we are going to do is to make superposition. Energy for 3 meters per second first, half rho A V cube, and delta T is 50. And V is 3 meters per second, you get 827 watt hour. For the other 50 hour at 9 meters per second, so the energy at 9 meters per second when half rho A V cube times H, or times delta T, which V is 9 meters per second and delta T is 50 hour, so you get 22,326. Then we add them together to get the total amount of energy generated. So you get 23,152 watt hour. So it's too much compared to this, to the previous case in one. This why because the wind turbine operates for 50 hours at higher speed. Once the speed is higher, so the output generated power is higher. In the next section, we'll talk about the temperature and altitude correction for air density. Temperature correction for air density. When wind power data are presented, it is often assumed that the air density is 1.225 kilogram per meter cube. It is assumed that the air temperature is 15 degrees centigrade and the pressure is 1 atmosphere. Using the ideal gas law, we can easily determine the air density under the other conditions. What will happen when we give you different atmospheric pressure or different temperature or different, so the power density will change. The air density will change. So from the ideal gas law, BV equal nRT. What is B? Absolute pressure. What is V? The volume. What is N? It's a mass. What is R? R ideal gas constant. And T, what is T? The absolute temperature in Kelvin. So when you change the temperature or the pressure, you end up with different volume and mass. If we let molecular weight, MW calls molecular weight, stands for the molecular weight of the gas, gram per mole, we can write the following expression for air density rho as. So rho now, the expression for rho, kilogram per meter cube, becomes N moles times the molecular weight, MW, gram per mole, times 10 to the power negative 3 to convert from kilogram to gram, and divided by V, the volume, meter cube. So you end up with P times mw times 10 to the power negative 3 over RT. That means when the temperature change or the pressure change, the density of the air will change. It will not remain constant like 1.225. So all we need is the molecular weight of the air, which is 28.97 gram per mole. So the molecular weight becomes constant, R is constant. The only two unknowns are the temperature and pressure, so then we can calculate the density of the air. So example, find the density of the air at 1 atmospheric pressure and 30 degrees centigrade, or 30 degrees centigrade, or in Fahrenheit you have to add 273, so you end up with 86 degree Fahrenheit. This is the Fahrenheit. No, in Kelvin you have to add 273 to the 30, you get a degree in Kelvin. So now the atmospheric pressure is given and temperature is given, so the only unknown is the density. So density becomes 1 atmospheric pressure times mw is a constant, 28.97, times 10 to the power negative 3 divided by R is constant, R 8.2 times 10 to the power negative 5, times the temperature in Kelvin, so you have to add 30 to 273, then you end up with 1.165. So the density of the air decreases by 5% since the temperature increases from 15 degrees centigrade to 30 degrees centigrade. Since which is a 5 degree decrease in density compared to the reference 1.225, since the power is proportional to density, it is also a 5 degree centigrade, 5% decrease in power in the wind. So this is the effect of changing the temperature of the wind turbine on the air density, and then it will affect the power of the wind. This table shows the density of dry air at a pressure of 1 atmospheric with different temperature. So this is the effect of temperature on the density of the air. So the temperature negative 15 degree to 40 degree. What happened when the temperature very low, the density of the air 1.368, which is bigger or greater than the density of the air at reference value, which is 1.225. So the density ratio, it's greater than 1. When the temperature increases, the density ratio drops and reaches to 1 at our reference value at 15 degrees centigrade. The density becomes 1.225 and the density ratio is 1. Once the temperature increases again, the density decreases, and then the density ratio decreases less than 1. Now we'll talk about the altitude correction of air density. So first of all, we talked about the effect of temperature. Now we'll talk about the effect of height or altitude. So the air density and hence the power in the wind depends on the atmospheric pressure as well as temperature. Since air pressure is a function of altitude, so it is useful to have a correction factor to help estimate wind power at sites above the sea level. And here we can see that suppose that you have a weight of slice of air with rho g a delta z, and its area A, and there is a pressure on top P of Z plus delta Z, and the pressure of bottom P of Z, which is B of Z plus delta Z, plus the weight G rho delta Z divided by the area. And its length delta Z here. And it's this slice of air is located at Z distance above the ground or the sea level. Then a horizontal slice of air in that column of thickness delta Z and density rho will have a mass rho A delta Z. If the pressure at the top of the slice due to the weight of air above it is B of Z plus delta Z as we mentioned before, then the pressure at the bottom of the slice P of Z will be P of Z plus delta Z plus the added weight per unit area of slice itself. So BZ becomes BZ plus delta Z plus rho A G A rho A delta Z divided by A. So you end up with J rho delta Z. So delta B, we know that we can write the incremental pressure delta B for an incremental change in elevation delta Z. So delta B, as we know, P of Z plus delta Z minus P of Z. That means equal minus J rho A delta Z. Minus J rho delta Z. If we look for the differentiation, the rate of change of P with respect to the height or the elevation delta Z, so it becomes minus J rho, minus rho G. So the air density rho itself is the function of pressure as described in this function, in this equation. So we can rewrite again delta B by delta Z in terms of G minus G, and rho becomes molecular weight times 10 to the power negative 3 over RT times B. Then the pressure, the solution of this equation is pressure equals P naught. P naught is the reference pressure at 1 atmospheric pressure. E to the power minus 1.185 times 10 to the power negative 4 times H. What is H? H, the height in meter. That means the pressure equals 1 atmosphere times e to the power minus 1.185 times 10 to the power negative 4 H. So once we know the height, we can calculate the pressure. Once we know the pressure, the new pressure, we can calculate the new air density from here, because rho depends on P. Once you know the value of P, we can calculate the new value of rho, and then we can calculate the power from the wind. Let's take an example. Example 4, find the air density at 15 degrees centigrade. This is the reference temperature at an elevation of 2000 meters. That means at that height, the pressure will not be 1 atmospheric pressure. So we need to calculate the new pressure, and then we need to calculate the air density rho. How to calculate? First, we need to calculate the new pressure from here, and then we use it to calculate the new density from here. Then find it assuming an air temperature of 5 degrees centigrade at 2000 meters. Okay, first of all, we consider H is given at 2000 meters, so we put here H 2000, we calculate B. So B becomes 0.789 atmospheric pressure, not 1. So P is different than 1, MW is constant, R is constant, T is 15 degrees centigrade, so we can calculate the new rho. So rho becomes 0.967 kilogram per meter cube instead of 1.225. In the second part, both temperature and pressure will change. That means the temperature will not remain at 15, it becomes 5, only 5 degrees centigrade. So when the temperature change, so we need to put the different temperature here. Instead of 15, you put 5 plus 273 in the low, you end up with 1 kilogram per meter cube. That means at that height, both pressure will change, will reduce, and the temperature also will reduce. That will make the density of the air will reduce, will be decreased, instead of 1.225 to 1 kilogram per meter cube. Once you know the new value of rho, you can proceed to calculate the power from the wind. Here is, in this table, it shows the air pressure as a function of altitude. So this altitude in meter from 0 to 2 kilometer, 2 and 2,200 meter. And this is in feet. This is the pressure, start with 1 atmosphere at sea level and then decreases when we go higher, goes up. And the pressure ratio actually start with 1 and decreases. What is the pressure ratio? Pressure ratio actually, it's pressure ratio. Now we can embed it in the equation. A simple way to combine the temperature and pressure correction for density is as follows. Rho equals, we can write it down as rho equals 1.225 times Kt times Ka. What is Kt? The correction factor for temperature. What is Ka? The altitude correction factor for altitude. And they are tabulated in these tables. So Ka is the pressure ratio from here, and Kt, we can go back to this table, we can see Kt is here. So Kt is the density ratio, while the Ka is the pressure ratio. Once you know Ka and Kt, you can embed it in this equation, you can find rho. Let's see this example. Example 5. Find the bar density in 10 meter per second wind at an elevation of 2000 meters and a temperature of 25 degrees centigrade. Compare that to the power density under standard conditions, 1 atmospheric pressure and 15 degrees centigrade conditions. First of all, we need to calculate the power density. So at that height and that temperature, so we need to calculate the new density of air. So we are going to use the expression for the density of air. So at that height and that temperature, the density of air becomes 0.9415 from the previous equation. Then the power density becomes half rho v cube, which is the power divided by the area. So the power density half rho v cube. We calculated the new rho and we know the velocity or the speed of the wind 10, so we get 470 watt per meter square. But in under standard conditions, 1 atmosphere and 15 degrees centigrade, we are going to use the formula directly, half rho v cube, and rho 1.225, so you end up with 612 watt per meter square. So there is a difference between the real power captured and the reference power at standard condition. So there is a 23% decrease in power density at higher elevation and temperature. This is actually the end of our first presentation on the wind turbine. Thank you for your